You might have seen this demo before, where a person takes a permanent magnet and drops it through a pipe that's not ferromagnetic whatsoever. In this case over here, this pipe is made up of aluminum. But have you seen how it falls inside the tube? It's rather hypnotic. Often this demo is known as Lenz's law demo or the cow magnet demo, because often you take a big cow magnet and drop it through here, and it takes longer than a fraction of a second for it to fall. All right, and today we'll be talking about the adventures of induction current. What I have over here is a solenoid, nothing inside of it, air core solenoid, connected to a device called a galvanometer, which can tell you which way current is flowing, whether it's flowing this way or the opposite direction. So if I take this magnet here and I push it through the solenoid, you'll see that the current flows one way, and as I pull it, the current flows the opposite way. What Lenz's law is stating is that this device over here, even though you can't see it, there are magnetic fields that are passing through it, and it's happy with the state that it's in its ether of B fields. However, if this party crasher comes by, it's going to disrupt that native B field. This guy says, "No way, Jose, I don't want to see any change," so it fights back. And the only way it can fight back is by turning on into a solenoid, pushing against the changes in motion of the first magnet. But in doing so, while it's turned on, it induces current. All right, so that's the induction of current. Moreover, if I take this magnet and I flip it the other way around, you'll see that the needle goes in the opposite direction now. All right, so this time around, it's going in the same direction that I'm pushing and pulling, but if I flip this around, it's going to go in the opposite direction. All right, so the orientation of the magnet being pushed into the solenoid does change your outcome. Once again, you need to have a changing magnetic field in order to induce current. So you can see that as I pull this, the red LED lights up, and if I take this and I flip it the other way around, now the amber LED lights up. All right, now if I leave the magnet in there, nothing happens. Okay, I need to have a continuous changing B field in order to induce that current. This is the principle of how all induction chargers operate. Maybe you've seen these devices before, all right? For example, what over here is a cell phone charger, all right? However, it's waiting for a communications protocol to the second device. Yes, it's going to turn on the solenoid just temporarily, so they can induce a B field onto the second object, where it has a tiny little microchip, which will communicate a message all the way back, and that's the basis of how RFID works. Since this thing is nothing more than just a copper coil attached to a red LED, it doesn't have the smarts to tell it that this is a coil, so it only blinks. If I want this to light up indefinitely, then I'll probably want to place it in a dumber device, like this toothbrush charger over here. Even though you can't see it, there's a copper coil in here, and it's generating an AC current, or an AC current's passing into the coil. So the B fields are pointing upwards at one moment and then downwards at another moment. And as it penetrates through here at probably around 10,000 times per second, that changing magnetic field induces a current into this very simple electronic circuit. One more thing I can demonstrate with you with the circuit over here is that you can see that the relationship between the B fields and the opening here is in alignment with each other. All right. And as I tilt this, the brightness of the LED decreases to the point that when I'm at 90 degrees, it doesn't light up anymore. All right. Very similar to the cosine calculations. Cosine of 90 degrees is equal to 0, and a cosine of 0 gives you a 1, or the best efficiency possible. Yes, I could demonstrate that with this coil here as well. If I place this on top of the cell phone charger, you can see it's blinking, and both LEDs light up, indicating that there is a changing B field this way as well as the opposite way, and this is a continuous change in both directions. Yes, this is also the basis of how transformers are made. Transformers are really just two separate solenoids. The catch is that the second solenoid, or the primary coil, has to be connected to an AC power source. So let's turn it on. And to prove it to you that this is an AC power source, I'm just going to take this magnet here and bring it nearby. You can see that's vibrating like crazy as it's being sucked in and pulled out from this activated solenoid. So as I bring the second one near it, you should start to see it light up. Ja-ja! Now it should light up, however, this is a very terrible solenoid. All right, for one thing, this is an air core solenoid. So if I want to improve the efficiency of transfer of magnetic fields from coil A to coil B, I need to use something other than air. Probably can't tell on camera, but these two are two different metals. This one here is much lighter, it's aluminum, and this one is made up of stainless steel. Best way to prove that to you is by using a permanent magnet. You'll see that the aluminum is not affected by the permanent magnet, but the stainless steel rod loves it to death. I'm going to start off with the aluminum rod, put this through it, and you can see that it doesn't do much at all. All right. Aluminum is paramagnetic, so unfortunately it's not very good at transferring B fields. I'll replace it now with, oh, that's tough. With the iron core, you'll see that it's really good at transferring the B fields. All right, so once again, this guy over here is behaving as if it's a magnet, whereas it turns on. For example, in this case over here, if this is positive, then the current's going down, and this side will be magnetic north. This side over here says, no, I don't want to see any changes in the magnetic field because of this guy over here, so it's going to temporarily turn on and have a magnetic north point this way. In such, the current will be induced in the opposite direction, which then lights up the LEDs. One more demonstration I want to share with you is what if I switch this over from AC to DC now. All right, now the first moment I attach this, you'll see that it lights up, all right, because it's as if I'm placing a magnet into here. But since there's no changing magnetic field, there's no more current being induced. But if I disconnect it, you'll see the other LED light up. That's when the B field over here collapses. And as it collapses, there's a change in magnetic field. This guy doesn't like to see the change in magnetic field, so it still turns on as a solenoid, inducing current, lighting up the opposite LED. So I need to have a continuous change in current in order to induce current into the second coil. Before I end off today's adventures, just a big shout out to my very first Patreon. Thank you so much, Valentin, for supporting me. He also has an awesome website as well with regards to science fun. So if you have a chance, check out his channel. For more adventures like this, make sure you like, click, and subscribe, and I'll catch you in another day's episode.